Okay, good morning. We are recording. Happy Wednesday. We are reaching the end of the semester, and the idea is that we have today's class period. I have office hours on Fridays, so on Friday mornings, I can also Zoom and continue to help prepare any students that want to voluntarily log on for Friday for another session. Next week is finals week, so the idea is that what I'm planning on doing to help you guys out is that on Monday, I would hold a session just like we normally do, and it could be like your last chance to have any sort of prep, any sort of questions, any sort of review in general. That could be on Monday, which would be then our last class period. And then once that class is done on Monday, I would open up the final. And then you would have the option to take the final. You'd have the option you'd be required to if you want to pass the class. Take the final, and that would be the plan of attack that I'm thinking about or looking at. So yeah, good morning, Wednesday. Other administrative things, you know, if you're wanting to get into summer school classes, I'm starting to do a lot of emails back and forth. So if you're trying to get registered for classes, shoot me an email if you're interested in that. With that, I just kind of open it up to the group. I have some possible questions that I've brought in that I don't mind, you know, covering and going over with you. You know, some things that kind of relate to, you know, the end of the book, you know, some of the math and performance and weight and balance, some of those types of questions. But I also don't mind fielding the questions that you've been working on. So, you know, a lot of the time this semester, you've been doing practice written submission assignments where you take practice writtens and you write down the questions that are troubling you. So I don't mind going over those. They're probably a lot of the same questions that I'm thinking about are probably the same ones you are. So with that said, you know, good morning. It's kind of an open floor. If there's any questions from the class, any sort of input, you know, now's a free open time for anybody to speak up if there's anything that's on their mind. All right, well, we're not getting a lot of participation. The idea is I think maybe there's 5 questions left from weather that we were going to review. So maybe we'll review those 5 questions from weather, and then I'll kind of launch into some of the other questions that we might possibly see coming up. Okay, so I'll hit the share screen button. And at this point, you guys should be seeing my Blackboard, which has weather. I think we left off here at number 60. To best determine general forecast weather conditions covering a flight information region, the pilot should refer to graphical forecast for aviation. Okay, so what's the problem with these other two? Weather depiction chart, satellite map, both of those are historical observations. They are not forecasts. So we're truly trying to get the difference between historical weather products and forecast weather products. So that's why graphical forecast for aviation is the best answer. If you end up seeing some of the older questions in the FAA test bank, the correct answer for some of the older questions might be area forecast, but now they've discontinued that product and they're getting into the graphical forecast for aviation. 61, what is indicated when a current convective segment forecasts thunderstorms? And the most correct answer, according to the FAA, thunderstorms obscured by massive cloud layers. You know, I like answer choice B. I think answer choice B looks good, but according to the FAA, the answer choice C is going to be the better answer. Thunderstorms obscured by massive cloud layers. Okay, when speaking to a flight service weather briefer, you should state, the best answer choice here is whether the flight is IFR or VFR. So, for example, if you're an IFR pilot and you're taking an instrument flight, that's important information the weather briefer needs to know. Because if you was a VFR non-instrument pilot, then that weather briefer might want to tell you VFR not recommended. That weather briefer might beg you not to go. So if you're an instrument pilot, that could really affect his recommendations for you about to go or no go. You know, summary of your qualifications, the pilot's commands, full name and address. I think the answer choice B, a summary of your qualifications, that's a distractor. That's a wrong answer anyways. That's not something that's on the FAA flight plan form. The pilot command's full name and address, that is something you will eventually have to tell the weather briefer, but your name and address is probably not really affecting the briefer's, decision about whether to tell you whether it's recommended or not recommended to go, no go. So whether you are going to take a VFR or IFR flight is the best answer choice here. All right, 63, when telephoning a weather briefer facilities for pre-flight weather information, a pilot should state, same idea, same question, but this time we have 3 new answer choices. So the best answer choice is the aircraft identification or the pilot's name. That is the best answer choice here, according to the FAA. All these other answer choices are correct. The weather briefer does need to know what your true airspeed is going to be. The weather briefer does need to know how much fuel you have on board. However, there's a difference between filing a flight plan versus receiving a weather briefing. So if you're filing a flight plan, it's going to be a longer phone call. You're going to have to give extra information to file that flight plan. Whereas you could call that same weather briefer and you say the words, I'd like to get a weather briefing. Well, then all of a sudden, the weather briefer could ask for less information and they could still give you a weather briefing without necessarily filing the flight plan. So to give a weather briefing for pre-flight weather information, the weather briefer is going to at least need to know the tail number, the aircraft identification number. And that's a common question that you get on the days of check ride. They ask, how do you know if you've officially checked weather? And there needs to be some sort of receipt of your tail number. You have to somehow input your tail number. That's the old buzzwords that's going to help you get through a lot of those questions. So right there, that's the best answer choice here. Okay, what should pilots state initially when telephoning a weather briefing facility for pre-flight weather information? Again, same type of question, but we now have 3 new answer choices. The FAA says, with these 3, the best answer choice is the intended route of flight and destination. So I agree, B, the address of the pilot in command. Yeah, that information's on a flight plan form, sure, but the weather briefer could still give you a weather briefing without that information. The weather briefer would need to know what's your route of flight, where are you flying to. It could be a completely different weather briefing if you say to the weather briefer, today I'm flying to Michigan versus I'm flying to Georgia, versus if I'm flying out to Iowa. So if you're flying different directions, that's going to affect your weather briefing. So the route and the destination are going to be the more important, better answer choice than the address of the pilot in command. In fact, on a lot of the FAA flight plan forms, a lot of the pilots write down the words on file at EYE. So if you write down your name and your contact information, your phone number on your flight plan form, and you speak that to them on the phone, instead of reading your whole address, a lot of pilots will say the words, I'm on file at EYE. So that means if the FAA or the weather briefer had to pick up the phone and call the Eagle Creek Airport, they could find some file somewhere at that airport that has your address on it as well. Answer choice A, the intended route of flight radio frequencies. Well, yeah, the weather briefer would need to know your route of flight, but the weather briefer does not need to know what radio frequencies you're going to use. So that's a distractor answer choice. The best answer choice here is the intended route of flight and destination. And the last question we're reviewing here for weather, which type of weather briefing should a pilot request to supplement mass disseminated data? And they're saying the best answer choice is an abbreviated briefing. So we have these other answer choices of an Outlook briefing. Well, yeah, Outlook briefing is going to be if your flight is more than 6 hours in the future. This question doesn't say anything about more than 6 hours in the future. A supplemental briefing, that is a distractor type of answer. There's no such thing as a supplemental briefing. So that's why the answer choice abbreviated briefing is the best. So this has been us reviewing some of the questions from our weather studies. And as we move forward, we're going to start thinking about some of the questions that we might find later in the book. And so what I'm pointing out to you guys are seeing my Blackboard. I'm going to come over here to content. And when you look in the content folder, I sent out an email about this as well. And you guys have had access to this, so you can just click around in here. And the whole idea is down here at the end, I have a folder set up for you guys. It says final exams. So when you click in here in your final exams folder on the Blackboard, here's the actual final exam I'm building for you right now. And on Friday during my office hour, I had a student call in and we did some math problems together over weight and balance. So I hit record and I uploaded that here. So if you're struggling with one of the weight and balance fuel burn math problems, you know, there's about a video here you can check out. Here's a PowerPoint that I've put together, you know, for possibly today that, you know, could walk us through some of the tricky problems that we've been working on. And what you're finding here is that we have practice exams. So what you can do is you can click in here in this practice exams folder, and you're going to find 11 different practice exams. You don't have to do any of these, but if you're a person that's worried about your final, if you're a person that's worried about your grade, you're a person that wants to study up, which is a good idea, you should do that. You can take practice exams right here. So all semester, I've been encouraging you guys to use like the Sporty Study Buddy software. That's very equivalent. I would recommend Sporty Study Buddy. Lately, I've been finding myself on the Exams for Pilots website. They have a lot of good practice exams. And right here on your own Blackboard site, you don't even have to leave your Blackboard site. You can find 11 different practice exams. So a lot of these are from old semesters. You know, you imagine semesters and semesters ago, there were multiple exams and the exams keep updating every semester. So you can look through here and take some of the old practice exams. You can take some of the old exams for practice. Traditionally, this course would typically offer multiple final exams. That's not going to be the case this semester. My boss has said that for this course, we will offer only one final exam. So in this course, we'll have one final exam. And when that final exam comes, you will find it under content, final exams, and it'll say final exam, spring 2020. And that'll be our one final exam for this course. That'll be used to compute your grade for this course. It's one of the factors that goes into your grade. And if you are able to, you know, pass this course, you'll have a graduation certificate, and that graduation certificate can qualify you to take the real FAA written exam. You've already paid to take the real FAA written exam, so that'll happen through us, Vincennes University. But because of a lot of the issues of us not being able to proctor the test and make sure that nobody's trying to cheat, ethics, that for you to actually take the real FAA written exam with us, with Vincennes University, you will have to come to the computer lab after operations open up and we're allowed to allow people into the computer lab again. You'll come into the computer lab and you'll have to take some practice tests and you'll have to prove your ability to perform, you know, above 80% on multiple attempts. And then after you've done that, then Vincennes will administer the real FAA written exam to you. So those are the instructions that I've been given from my boss. I'm passing them on to you about how that's going to work. And what I'm going to show you is that here in content and in the final exams folder, I'll have some possible questions might be good for us to go through. And I don't mind opening that up and starting to head through those, but I also don't want to leave any unanswered questions. So if anybody has any questions about anything, now might be a good time as well.
Hey, real quick, Mr. McKinney, are
Of
we?
course.
I don't know if you've already answered, and if you have, I'm sorry. Are we supposed to do like chapter 8 homework and stuff, chapter 9 homework and stuff, chapter 10 homework and stuff?
The word is extra credit. Okay. So if you are a person that wants extra credit in the class, I am accepting, you know, 8, 9, 10. So there are chapters at the end of the book that chapters 8, 9, and 10, those are voluntary extra credit points. It's good for you. You know, I would, you know, recommend you to do those assignments if you would like extra credit points, but I'm not going to penalize you. So if you're a person that's still struggling to finish up the other required assignments, the required, the assignments that we've done for chapters 1 through 7, vocabularies, homeworks, short answer questions, homework assignments. If you're a person that has yet to complete those assignments, I would recommend that you would go back and complete those assignments and get those points. And then if you're a person that's already completed all the previous homework assignments and you desire extra credit, well, then you have extra credit opportunities if you wanted to work on any of the assignments for chapters 8, 9, or 10, if that answers your question.
Yeah, it does. Thank you.
Mm-hmm. And really, one of the best things you could do is just take practice writtens. Because like in chapters 8, 9, and 10, every single one of those folders, there's one of the assignments is take a practice written. And that's what, this whole class is about, is trying to prepare you for the written exam. So, I mean, you can just take some practice writtens and, grab a few extra credit points that way as well. Good questions. It's an open floor if anybody has more questions for us. So I'm clicking the buttons that's going to launch this presentation here. We don't necessarily have to follow it slide by slide, but these are just a few of the questions that I've been thinking about that might be good for us to spend some time on. So we have today, let's see, clicking buttons. Cool. So I clicked this button. And as we get going, if you're a person that really hasn't spent much time with like your E6B, your whiz wheel, or your plotter, those are some things that, could be worthwhile. Some of the best things, it's called flight planning, the ability to plan flights. And I want to try to make it really simple for you. This is my plotter. And so there'll be some questions where you have to plan flights. And so like, for example, like, there's a sectional chart, and you put your plotter up against the sectional chart and you connect your airports, you line them up. And then on this one, you can spin the wheel. And when you spin the wheel, that's how you can discover the course. Some of the plotters do not have a spinning wheel. So if that's the case, then you just read the number on the plotter. I want to try to walk you through some of that. I think it's going to happen as we cover some more of these questions. This is the E6B, the whiz wheel. This is a flight computer. It's basically a slide ruler. And so basically you spin the wheel, and then as you spin the wheel, it does math for you. There's going to be some inner windows that can line up and show you some of that information as well. And if I just give you kind of a quick and dirty lesson about the E6B, the whiz wheel, it's the biggest thing that you need to remember is that we as Americans, as human beings, we don't always operate off of a 10 system. We don't always operate off of a 100 system. For a lot of this math, we operate off of a 60 system. Our base is 60. Like think about how like there's 60 seconds in a minute. There's 60 minutes in an hour. So with a lot of the math involved, you're going to have to use 60 as your base. So that way when you hit 60 seconds, that's considered a minute. When you hit 60 minutes, that's considered an hour, which is different than traditional math where when you hit 10 or 100, that's your base. So that's why you notice on your E6B, your whiz wheel, when you really start studying this thing, there's a big arrow. There's a big arrow on your whiz wheel, and that big arrow lines up with the 60 number, because here's 55, and then that big arrow is the 60, and then there's a 70. So when you're using the E6B whiz wheel, some of the best things to do is really pay attention to 60, because that's your base. And if you're moving 60 miles an hour, then that means you're moving 1 mile a minute, 60 over 60. If you're moving 2 miles a minute, well, then your base is 60, but it's actually 120 over 60 because you're moving in 60 minutes, you move 120 miles. And that's what we talk about with knots. So like if you're traveling at 120 knots, that's 2 miles a minute. So I know it's going to be difficult for me to do this with the camera, but I'm just going to try to help you out a little quick. So what I'm explaining to you about this whiz wheel is that there are scales. You have an inner scale and you have an outer scale. And you can spin the inner scale and you can line up the inner scale to align with a value that is on the outer scale. So what I need to tell you, what's really going to help this out a lot. The inner scale is always time. If you're taking notes, that's really important. The inner scale is always time. The inner scale is always time. You'll be amazed that if you can just remember that, it's going to help you a bunch. The inner scale is always time. So that means your outer scale is going to be things such as weight, fuel burn, gallons, minute, not minutes. Time is always on the inner. Okay, so I've tried to walk you through some of that. Each whiz wheel, each E6V has the instructions literally printed on the front of your whiz wheel. And I know it's probably difficult to read this, but if you pull out your own whiz wheel and study it, you can read the instructions right here on the front of the whiz wheel. And so that's going to be one of your best tools, is reading the instructions on the front of your whiz wheel when you're trying to do the math. And I can walk you through some of it as well. Same thing's going to happen on the back. This whiz wheel is a little older. Yours is probably newer. It's probably better. But the instructions are literally written on the back. So when we start doing some of those problems, that'll be one of the better pieces of advice I have for you. Okay, so fair enough. Let's see what happens if we open up some of these questions that we might possibly see. So I hit this button. Okay, but you're not seeing it. I did something wrong. How about this button? Cool. All right, I think you guys are seeing it. I'm hitting this button. It's going to work. Aha, we're going. Okay, so here's some possible questions involving some of the math and flight planning we need to wrap our head around as private pilots. So this question right here, it talks about what fuel flow should a pilot expect at 11,000 feet on a standard day with 65% maximum continuous power. Okay, so it says that we need to reference figure 35. So I've already created that in the slide. So if I click to the right, this is what figure 35 looks like. And we kind of covered this a little bit quickly the other day. And this is a cruise power setting chart. And so you can get an idea based on what altitude you're cruising at over here on the left where my mouse is moving, based upon what altitude you're at, and then other factors such as standard day or ISA, International Standard Atmosphere, plus 20 Celsius. That means it's a really hot day. You could call that plus 36 Fahrenheit. Or over here on the left side, ISA, International Standard Atmosphere, minus 20 degrees Celsius. That'd be a really cold day. So if it's like a standard day or a really hot day or a really cold day, or if you're at a higher or lower altitude, then all of a sudden you might find different performance information. You might predict different performance information for your aircraft. So in this example, it says refer to figure 35. What fuel flow should a pilot expect at 11,000 feet? So we got to know that, 11,000 feet on a standard day. So it's not extra hot, it's not extra cold, with 65% maximum continuous power. Well, this whole entire chart is showing us 65% maximum continuous power. Okay, cool. And it said standard day. So we're only going to deal with this middle section right here. This is where we're looking. And again, with every figure that you look at, you always want to read the legend, the chart, the notes. And down here, some of the notes are full throttle manifold pressure settings are approximate. And it says the shaded areas represent operation with full throttle. Well, in this case, the chart didn't give us a whole lot of good information, but if I was you, I would still read all the notes before you ever start to tackle a problem, because sometimes it gives very important information. Okay, so we're at 65% maximum power. We're on a standard day, and we just said we're going to fly at, was it 11,000 feet? So we don't have information for 11,000. We have information for 10,000 over here on the left where my mouse is, and I have information for 12,000. We do not have information for 11,000. So that might involve math, where we have to do what's called interpolation. So interpolation means that we have a known value for 10,000, we have a known value for 12,000, and we have to do math to figure out what the middle value would be. There's a lot of different ways to do the math for interpolation, and we may or may not have to do some of that math today, but the most simple is if they're perfectly in the middle, add them together and divide by 2. That's the most simple interpolation. It can get much more complicated depending on how fancy we're trying to be with our interpolation math. All right, so we've established that it's standard day. We've established we're at 11,000 feet, and the question was, how much fuel flow do we expect to burn? I think that was the question. So I'm comparing these two numbers right here. So, you know, IOAT, I'm gonna explain all these to you real quick. IOAT, that stands for indicated outside air temperature. So OAT is outside air temperature. You see that a lot in aviation. IOAT was indicated outside air temperature, and that's why it's telling you Fahrenheit and Celsius. We have engine speed, RPM, revolutions per minute, how fast the engine's spinning. We have manifold pressure, that's inches of mercury, so that's how much air pressure is coming into the intake manifold. So power going into the engine, the amount of air coming into the engine, how thick the air is coming into the engine. And then this is what I think we're really looking for, which is fuel flow per engine. We have PSI, pounds per square inch, and then GPH, gallons per hour, which I think is more of what we're looking at, gallons per hour. And then TAS, which is true air speed. TAS could be knots, KTS, or miles per hour, MPH. Okay, so now that I've explained it all to you thoroughly, 10,000, 12,000, those are the altitudes that we're analyzing. And what we're getting is we're getting different numbers of possible gallons per hour for 11.5 or 10.9, depending on what altitude we fly at. So if I can, let's see if I can start typing on the screen and do some of this quick, dirty math for you. So if I have 11.5 gallons per hour at 10,000 feet, and then I have 10.9 gallons per hour at 12,000 feet, what is the gallons per hour at 11,000 feet? That is the exact math problem that we're trying to tackle right now. There it is. I laid it out for you. So how are we going to do that? Great question. I'm glad you asked. So I'm going to say 11.5 plus 10.9 equals, and then I just type it into my calculator right here that's in front of me, 11.5 plus 10.9, because I'm a human and I can make mistakes. If I punch it in the calculator, there's a less chance I could do that. 22.4. Okay, then I divide by 2 because I want to know the exact middle of those. So divide by 2. And it's 11.2 just looking at it, but I guess I should type it in my calculator as well. 11.2. So that would be the gallons per hour at 11,000 feet. Okay, so I think I did it. I think I explained it. I'm thinking that's the answer. If I go back, oh, come on. This button. This button. Okay, and that's why you get the correct answer of 11.2 gallons per hour. And then here's my work in blue, which is typical to see. There it is. And that's me covering the first question here. Thoughts, questions, comments?
What is the easiest way to access that chart?
Great questions. Okay. So let me clear my annotations, clear all my drawings. Okay. I'm hitting the escape button. Come on. Oh, I got to hit this button. Stop share. Okay, I'm getting closer. It's still on my screen though. Okay, now I got you. What is the easiest way to access that chart? Okay, at the beginning of the year, one of your guys' required course materials was to buy some sort of test prep book. And so like this is the one that I have, which is the ASA version. And it actually has included with it the figures of all the legends and the figures. So if you have purchased the test prep book, then you probably have a physical copy. And this is great. It is so nice to have a real physical copy that you can open up and breathe and smell and write on, take notes on. Although on the real final, on the real FAA test, you can't write in this book because you screw it up for other test takers. But if it was your own personal book and you wanted to write in it, although you're not supposed to, but maybe you're a person that's pinching your pennies and you didn't buy the books like you're supposed to, gosh, well, it doesn't mean you're totally screwed. So what you can do is go to the FAA's website. So I'm going to click the button to show you that. So here I am, and we go to www.faa.gov. And when we get to the FAA's website, what we're really looking for is that document. That document is called Airman Knowledge Testing Supplement for Sport Pilot, Recreational Pilot, Remote Pilot, and Private Pilot. That's what this document is called. So you are seeing my screen, I believe. You're seeing the FAA website, I think. Maybe?
Yeah.
You are? Okay, okay. So I got a search bar right here on the FAA website, and I type in test supplement. I don't know. Let's hit search, see what happens. Okay, there it is. The first hit that comes off the FAA website is computer testing supplements. So I click computer testing supplements, and it loads up, and you got to find what test you're studying for. You are pilots and instructors, and you're not commercial pilot. Here's you. You are private pilot, the middle. I click it, and it's going to download, and it's a PDF download. So if you have not downloaded this document, you should. So that way it's already on your computer. You don't have to try to fight the internet. Just download it, save it in a folder on your computer, and then whenever you're taking practice writtens, sometimes they pop up the picture, the written figure that you're asking about. Other times they just say reference the figure, and you need to have this document to be able to find that figure. It's kind of a big PDF document, so it's kind of taking a minute to load up on my end. I've actually already downloaded it on my computer, but I hate to exit out if you haven't seen it. So here it is, 113 pages in all of its glory. There's a digital copy. And we've actually opened this up and looked at it before in class together. Is this answering any questions, or is that confusing?
Yeah.
So for today's sake, I'm going to exit out because I actually already have one of those loaded up right here that came off of my computer that's already downloaded. And then also in this slideshow presentation, I already included a lot of those figures as well. Okay, so let's see if we can tackle this next one. This one's a lot of the same ideas, just it's going to involve a touch more math. So this next one also uses figure 35. What is the expected fuel consumption for a 1,000 nautical mile flight under the following conditions? We're supposed to use that exact same figure, figure 35. It says our pressure altitude is 8,000 feet, our temperature is 22 Celsius, our manifold pressure is 20.8 inches of mercury, and the wind is calm. Okay, cool. So we need to remember, what do we need to know? We need to know that our altitude is 8,000 feet. We need to know our temperature is 22 Celsius. We need to know our manifold pressure is 20.8. And I got a bunch of like sticky notes and scratch paper over here at my desk. I'm really tempted to just kind of write that down right now. You know, just some chicken scratch, just so that way I can have that information handy in front of me. So that way I don't have to keep going back and forth. Okay, so I got that information documented on a piece of scratch paper in front of me. So now I'm going to go check out the figure. Here's my figure. So I told myself that I'm asking about 8,000 feet. It's nice because they give us the 8,000 number. We don't have to do any interpolation. It's just going to be exactly the 8,000 number, it looks like. And it says 22 Celsius. Well, check this out. Here is this middle is my standard day. The left column, ISA minus 20 Celsius. That's one extra cold day. Over here on the right, International Standard Atmosphere plus 20 Celsius. That'd be a really hot day. So IOAT, indicated outside air temperature. We are going to be at the altitude of 10,000 feet. I wrote that down. Nope, I just said it wrong. We are at the altitude of 8,000 feet. Thank you. We're at the altitude of 8,000 feet, and it tells us that we're going to do 22 Celsius. Well, at 8,000 feet, if I use the standard day column, 8,000 feet, that says that my Celsius is 2 degrees Celsius. Well, that's no bueno. That's no good. We said we needed 22 Celsius. Well, like a fool, I can look over here to the left. The left is an extra cold day. At 8,000 feet, it says my temperature on an extra cold day might be -19 Celsius. That's not what I want. What if I look over here to the right? On 8,000 feet, if I follow my mouse over 8,000 feet, hey, look at this. It says 22 degrees Celsius. Hey, this is looking pretty good. As I can continue consulting my notes, it said that I have a manifold pressure of 20.8 inches of mercury. So over here on the right, I'm lined up on the 8,000 row. I'm lined up on the 22 Celsius. I'm lined up with a manifold pressure of 20.8. 20.8 inches of manifold pressure. That's my power setting. And so this right here under my mouse is all the information that I'm going to need to do the math. Okay, cool. So what information do I need to do this math? Well, right here, my GPH, my gallons per hour, is going to, and I should text this instead of writing it on my piece of paper so you can see. So I'm going to start annotating. I got to go back. I just remembered I missed a piece of the information. What's the information we needed? A 1,000 nautical mile flight. So that's what I need to remember. So let me write that down. 1,000 nautical miles. Okay. So I come over here and I'm going to start typing on the screen for y'all. I text and it's going to work. Why is it fighting me? Okay, I see it. Click. Okay, cool. So what do we know? We know that we're going to at 8,000 feet, we will burn 11.5 gallons per hour. Okay? And we will travel. Now you got to be careful. Was it statute miles, nautical miles? In this case, it was nautical miles. It said 1,000 nautical mile flight. So, and we will travel 8,000 feet. It looks like 164 knots. Okay. That's the information we needed to document to move on. So here's our information. And again, here's the 8,000 foot altitude. We lined it up and we're seeing that we're going to burn 11.5 gallons per hour. And we're going to travel 164 nautical miles an hour. Cool. So now the question arises, how much fuel will it take? Well, first, we need to answer, how much time will it take? Then we can figure out how much fuel. Okay, so that's me framing the question for you. Okay, so it's going to be 1,000 nautical miles to go at a rate of 164 knots, nautical miles an hour, nautical miles an hour. So there's different ways to do this math. Traditionally, we're supposed to use the whiz wheel, the E6B. So I'm going to try to show that to you. My mouse keeps disappearing though. There it is. So let me try to show it to you using the whiz wheel. And if you're a person that really hates this whiz wheel, you can just use a calculator. Okay, so now you're seeing my face. I lost my notes on the screen. That's a bummer. Okay, so here's my whiz wheel. Remember, the inner is always time. The inner is always time. We need to go from known to unknown. You have to go from known to unknown. What do we know? We know that we're going to travel 164 nautical miles every 60 minutes. So the inner scale is always time. So when I use this inner scale, see 30, 35, 40, 45, my inner scale, I need to focus on that big arrow. That big arrow is 60. The big arrow is 60 minutes. The big arrow is 60 minutes. Time is always on the inner, 60 minutes. It really could be 60 seconds, could be 60 hours, whatever unit of measurement you want to use. There are no decimal places with the whiz wheel. So we're going to use 60 on the inner end. We're going to call that 60 minutes. We want to align 60 minutes on the inner with 164 nautical miles on the outer. Right now, I'm not set up correctly because I got 60 minutes on the inner aligned with 21 on the outer. I need to align my 61 on the inner with 164 on the outer. There are no decimal places, so 164 really is the same thing as saying 16.4 or 1.64, however you want to line it up. So in this case, I'm going to try to spin the wheel. So I need to find 16.4 on the outer. There's 8. Just keep going. 16.4 is what I'm looking for. On the outer, I just keep spinning my whiz wheel. I'm almost there. I can't see it. Somewhere around in here, see 16? But I need 16.4. So I'm going to spin that inner wheel. I know, it's crazy that we're doing this over a camera, sorry. So I'm spinning my inner wheel to try to line up with 16.4. And it's really difficult. My wheel is really old and it's a bummer. So I just got to really press it hard. Use your muscles. Okay, so what I just did was I've lined up my inner 60, that'd be 60 minutes, with my outer of 164, because there's 16 and there's 17 and there's 5 clicks in there, so each one's worth 2. So I got it lined up with 60 minutes on the inner to 164 nautical miles on the outer. So here's something that's noteworthy. Are you ready? Once you have the ratio set, move your eyes, not the wheel. Say it again. Once you have the ratio set, move your eyes, not the wheel. So the idea is that we have the ratio set. The correct ratio is set, 60 minutes for 164 nautical miles. Now we're going to move our eyes, not the wheel. Well, we need to move our eyes to what? We're going from known to unknown. What we know is that we need to travel 1,000 nautical miles. The whiz wheel has no decimal places. So 1,000 could be the same thing as 10 or 1 or 10,000, whatever you need to line it up with on the whiz wheel. So in our case, we're going to line it up with the number 10. So again, move your eyes, not the wheel. So on the outer, I see number 10. And on the inner, I got to figure out what it's lining up with. I see that there's a 35 and a 40, and I'm between the 35 and I'm between the 40. It looks like 35, 36, 37, 38. Does it look like I'm lined up with 38? I think I'm lined up with 38. So 38, let's call that maybe 380. 380, maybe 38, 380, something of that nature. So let me document that down. So I lined that up with 38, maybe at 380, something of that nature. So let's see what we can do with our possible answers. Oh, that's right, we're on time. Okay, so 380. I lost my annotates. I wonder if I can come back. Nope, it disappeared. What a bummer. So we think it's going to be, so we anticipate 380 minutes to travel 1,000 miles. That's what I'm looking at right now. So 380 divided by 60. Just type it into the calculator. It helps prevent any sort of errors for you as pilots. We're not math majors. Oh no, Come on, calculator. 380 divided by 60. And I get 6.33. So it's going to be 6.33 hours to travel 1,000 nautical miles. Okay. We know that we're burning 11.5 gallons per hour. So I'm kind of interested to just go 11.5 gallons per hour times 6.33 hours equals, and I again type it into my calculator, make it simple on yourself, 11.5 times 6.33, and I get 72.79 gallons. Well, if I go back on a slide, gosh, and I didn't even get the right answer. Some of these are kind of tricky. What do you guys think I did wrong?
I think whenever you whenever you looked at the 35 on the whiz wheel,
Yeah.
it goes by increments of 2 instead of.
Aha. So, you know, best way to learn is to make a mistake. We're here learning. And we're saying that when we looked at
We're looking at the number 10, right? On the whiz wheel. Okay. So we're at least where I'm at. It's at because it says here on 35, 2 steps away. The seconds is every 2. So that would be 35, 36. Next 2 over would be 37. Next 2 over would be 38. Next 2 over would be 39. The next 2 over, you're 40.
All right. So I think that we're on a good path here. And the idea is that when I put this whiz wheel up to the camera, I'm kind of like looking at it through like a weird screen, you know? And so what he's saying, and I think he's exactly hitting the head on the hammer, is like, here's 35 and here's 40. So, you know, that would be like, that one tick would be like 35 and a half. The next tick would actually probably be like 36.
So it looks like it's 36 and a half.
So he's saying he's reading it as 36 and a half today. And I agree with you now. So it's a lot more clear now that I'm looking, you know, like hearing it. So 36 and a half is what we're thinking. So I wrote down 38. We think that it's going to be 36.5. So the idea is that click the button like that, and then click this button. And we think, click the button. Gosh, what a process. So we see on the whiz wheel, we see 10 on the outer scale, which is 1,000 nautical miles, aligned with 36.5 on the inner scale, which is time. So what's that really mean? That means we expect a 1,000 nautical mile flight to take 365 minutes to accomplish. So 365 minutes divided by 60 is going to equal, and again, just type it on your calculator, make it easier for yourself, 365 division sign 60, 6.08, 6.08 hours to complete, and then at a rate of 11.5 gallons per hour times 6.08 hours equals, again, just type it in the calculator. and I get a 69.995 gallons needed. So that's what I'm getting this time. And if I try to make this slideshow go back, yeah, I mean, I'm getting a lot closer to that 70.1. And that's kind of the bummer about these ABC multiple guess tests. You know, there's a lot of room for rounding errors. So all of a sudden, you know, one person who wrote the test might have rounded differently than you. Maybe somebody rounds way early, somebody rounds way late. But this one looks like a better answer. I think that if I would have had this, then, you know, I probably would have guessed the closest for the ABC. Which kind of really brings me to the big point of when you take your written exam, it's a timed test and they're all worth the same percentage. So some questions are going to be way more difficult and take way more time. You want to skip those questions and come back to them later because you don't want to burn yourself out fighting a question like this when there's a lot more simple questions you have to answer. So I appreciate the heads up there from Isaacs. I think he hit the head on the hammer, that you got to take your time to read the whiz wheel a little more clearly. What other thoughts, questions you guys have about any of those? So I'll go ahead and clear those notes, clear those drawings, and let's see what other kind of questions we could get ourselves into. A lot of these are the exact same. It's using the whiz wheel, so maybe we'll just do some of these. These are pretty simple as well. So this one says, how far will an aircraft travel in 2.5 minutes with a ground speed of 98 knots? So I'm gonna have to click down my screen share so I can show you my whiz wheel. So I just need to write this down. It's 2.5 minutes, and it's gonna be a ground speed of 98 knots. And the question is, how far? So here's like some of the notes that I put together for myself, and this is what I would do if I were you, because, you know, some of these problems can, you know, involve multiple steps. So just make a quick note to yourself, you know, what you need to do, how many minutes, what your ground speed, and the question is how far. So we got to go from known to unknown. What do we know? We know that we have a ground speed of 98 knots. So what's the ratio? We need to set this ratio up on our E6B whiz wheel. Well, remember, time is always on the inner. Time is on the inner. What is known? We know that we're going to travel 98 nautical miles in the course of 60 minutes. So on my whiz wheel, I need to line up my 60, which in my case is the big arrow, on the inner with an outer number called 98, which my 98 would be, here's 90 and here's 10. So you call it 9.0, you call it 90, you call it 900, you call it 9,000, doesn't matter. There are no decimal places on the whiz wheel. Call that 100, call it 10, call it 0.1, whatever you need. But the idea is I need to line up 60 on the inner scale with a 98 or a 9.8. I need to line that up. So here's my 60. I need to spin the wheel, spin the wheel. My whiz wheel needs lubricated. Fool me once, fool me twice. So I almost lined it up with the wrong number again. So in this case, you got to really pay attention. So here's like my 90 and here's my 100. And so you got to pay attention to how many click marks are in between on that outer scale. So in this case, I have 10 click marks. So each click mark is worth 1. So I believe I got it lined up. I believe I got it lined up with 98 on the outer and 60 on the inner. So the rule is, once you have the ratio set, move your eyes, not the wheel. So what do we know? We know that we're going to travel 98 nautical miles in 1 hour. The question is 2.5 minutes. How far are we going to travel in 2.5 minutes? Remember, time is always on the inner. Move your eyes, not the wheel. So we need to go to the inner scale and find 2.5 minutes. I would probably look for maybe 25, call it 2.5 on the inner. So here I am on the inner scale, I'm looking around. Oh, I'm almost there. So there it is. Okay, so on the inner scale, and it's backwards on my screen, maybe on yours too, but I got 2.5, and it's somewhere between 4.0 and the 4.5. And how many tick marks are there? There are big tick marks, there are little tick marks. I'm thinking I'm going to call it 4.1. 4. You guys think 4.1, 4.08, something like that? See how 25 is on the inner? What's on the outer?
Yeah, I kind of have to agree with you on that, but I don't know what I'm talking about either.
The only way to learn is to make mistakes and do it. So, you know.
Yeah, it looks like it's in between 4 point, like 40.5 and what would be 41. So yeah, 0.08.
Yep. So I'm going to call it 4.1 for today. I'm going to call it 4.1. 4.08 is what we actually said. Remember that? Okay. So we think we got an idea. Let's look at our possible answers. It says, how far will the aircraft travel in 2.5 minutes with a ground speed of 98 knots? The correct answer would have been 4.08. If you would have been a person that came up with an answer of 4.1, that probably would have been pretty close, and you would have clicked that one. And this bottom one here is the exact same principle. You know, we could go through that one, but we also got some other questions we might want to cover with our time as well. I don't want to leave us with any questions. I think we're getting pretty close to taking our bathroom break, but if there's any questions, we can answer those. All right, well, we're going to take 10. We'll be right back, and we'll be pumping through some more math and some more problems to help us out. We'll be right back. How you guys feeling? Did you get a snack?
No snack.
No snack. All work, no play. Well, we are at it. We are deep in the weeds. We are working on some math problems, some applications, some tricky problems that you might see on FAA tests. A lot of these problems are the questions that you would skip and you would come back to because they take more time. Today is Wednesday. We're halfway through the class. I have office hours on Fridays. So if you're still a person that's trying to get some more cramming in, Fridays between 9 and noon, we can log on and also be available at that time. And then Monday is finals week. So Monday I will open up our final, our test. My plan would be to open that up at like 12:30 or 1. It would kind of be a voluntary class on Monday. So if you're a person that wants to, continue getting some more practice, continue getting some more cram sessions in, continue trying to see some of these difficult, tricky problems come up, then Monday would be the last opportunity for it. I would say that it's kind of a voluntary because, it is finals week, so you don't necessarily have to log in on Monday if you don't want to. But I say that I would open up the test, open up the final following that class period. So on Monday, say 12:30, 1 p.m., somewhere in that ballpark, I'm going to open up the test. And I'll probably be able to leave that open until Wednesday evening is what I'm thinking. If there's a person that says they really need it open till Thursday, we can probably, accomplish that as well. Yeah. So I'm thinking probably Wednesday evening is probably when that would be open till, but if there's a person that's, communicates something they really need it to go up until Thursday, it's a possibility. Okay. Well, what do you guys think? Any feedback, good, bad, or ugly so far? You want to keep trucking? You want to see some more problems?
Yeah, let's keep trucking.
Yeah, definitely see some more problems.
Let's look at some more of these tricky problems that the FAA is trying to put in front of us. So here's a problem over here. This one's talking about takeoff distance. Gosh, we as pilots, it's important. We don't want to try to take off from a runway that's too short. Sounds like a bad idea. So every manufacturer has their own way of displaying performance data. So in this example, we're going to look at what's called, it says figure 40. And yeah, you're seeing my screen. Okay, yeah. So this is 40. And if I click the button, this is what the performance chart looks like. This is more of a Piper model. So if you're a Piper pilot, then this is what your performance chart looks like for takeoff. This is a Piper way of explaining takeoff distance data requirements. And the most important thing, again, with all these charts, all these figures, is to read the examples. So like the best thing you can do is just read through the example, read through the notes, read through the margins. They usually give you very good information. And I'm simply not going to be able to cover every single chart that ever exists with you. Piper, Cessna, Beechcraft, Cirrus, all these different manufacturers publish their data in a different way. And so what the manufacturer typically does is they put examples of how to work through their particular data. So in this example, you can see the red arrows. The red arrows are an example. And here's their example here. They had an outside air temperature of 15 degrees Celsius, 59 Fahrenheit, that's standard. And that's why their red arrow starts at this position of 15 degrees for outside air temperature. It says their pressure altitude, think about that as their field elevation. The field elevation they're taking off of, their pressure altitude, 5,650. So that's why you can see that their red arrow goes straight up until they get to this point, which they're calling 5,650. How did they decide that's 5,650? Well, because here's the 4,000 mark, and here's the 6,000 mark. And gosh, there's a lot of room for error here because 5,650 is just somewhere in this ballpark. And somewhere in that ballpark, when you get to 5,650, you go straight right to the next reference line. So there's the reference line. So we just accounted for a few things. We counted for pressure altitude, or altitude, if you will, and we accounted for temperature. Okay. we need to know information such as weight. Takeoff weight, 2,950, the next item here in the example. So you come over here to the reference line, and now we need to account for weight. In this example, the weight is 2,950. That is the maximum gross weight for this airplane, because here's your weights: 2,200, 2,400, 2,600, 2,800, and then there's 2,900, and it goes all the way to the line. And so if you did count it up the little boxes, that's 2,950. And so because we're at max gross weight in this example, the line just keeps going straight across. We don't need to account for weight any more beyond that in this example because we're already at max gross weight. Pretend you had a lesser weight. Pretend you were flying the airplane solo with half tanks and you were down at 2,600 pounds. Well, then you enter this reference line between these two big black lines. And so you would follow the same slope of those black lines. You'd follow the same distance, maintaining equal distance between them. Not equal distance, the same distance as you entered. So like here in this example, you entered just about in the middle. So you try to maintain about the same spacing and keep going down until you accomplish the weight that you're searching for. Once you accomplish the weight you're searching for, you just go over to the next reference line. If you can't see ahead, this is the answer ahead. Right over here on the right, see all these numbers, 1,000, 2,000, 3,000, 4,000, 5,000. That's how much runway you're going to need. So the idea is that every one of these steps is either going to bring you to a higher number or a lower number. So in this case, if I was at a heavier weight, I'm going to stay extra high. If I was at a lower weight, I'd follow the slope down to end up finding a lower runway requirement. In this example, according to their example in the top left, it says their takeoff weight is 2,950. That is the max gross weight. So they don't slope down at all. Their red example line just keeps going straight over to the next reference line. Now we're about to count for wind, headwind, or tailwind. We know that if you have tailwind, it's going to increase your takeoff distance. That's why the dashed lines, tailwind, come up at an angle, which will end up giving us a larger runway distance required, whereas the headwinds slope down to create a lower distance of runway required. In this example, in the top left, it says our headwind component is 9 knots. So we enter the reference line where this red meets, and it slides down until we reach the 9 knot. So here's 10, so 9, you slide down until you reach that 9. So we just lost some of the runway that we needed. We didn't need that much runway because we had some headwind today. So that's why our red line slopes down. Once we reach 9, then we go straight over to the next reference line. Okay, and from here, this Piper product in particular says obstacle height, feet. So what you're learning with takeoff distance information is that you could have different numbers. You could have something called ground roll, the amount of runway required just to get the wheels off the pavement, different than the words over a 50-foot obstacle. So most airports have an obstacle somewhere. I mean, really, unless you're a seaplane that's taken off from the water and there's no obstacles, or maybe like a plane in the desert where there's no obstacles other than a cactus every once in a while. I mean, there's usually an obstacle. Just about every airport, you know, has an obstacle somewhere nearby the property. You usually can't fly within one wingspan of the ground forever. You know, there's usually some obstacle. So, you know, as an instructor, I teach you that when you do real world takeoff distance problems, you should always just use the 50-foot obstacle requirements because you're going to need to get over a tree somewhere. It's a joke. They call it the FAA trees, 50 feet tall. So takeoff distance to clear a 50-foot obstacle. So takeoff distance to clear a 50-foot obstacle would require that we follow that same slope up to reach the 50-foot mark. If the math problem was asking you what's your takeoff ground roll, well, they're not asking about the 50-foot obstacle, so you could go red line straight over to get a smaller number of runway requirement. If the question on the FAA written exam is asking about takeoff over a 50-foot obstacle, well, then you need to follow that slope up to get the greater amount of runway requirement to clear the 50-foot obstacle. So that was me in depth walking you through this chart. And for today's sake, let's go back and look at our particular example. We want to work a problem that says determine total takeoff distance requirement for, I need to slow down. Determine the total takeoff required for takeoff to clear a 50-foot obstacle. Outside air temperature, standard. It's not too hot, it's not too cold. We know extra hot temperatures, the air is extra thin, you're gonna need more runway. We know extra cold temperatures, the air is extra thick, you get better performance out of the engine. You would use less runway. Okay, pressure altitude 4,000 feet. So this airport is not at sea level, it's up at 4,000 feet. We know higher altitudes, more thin air. More thin air means worse performance. So we anticipate we're going to see a greater amount of runway required with that. Takeoff weight, 2,800 pounds. We already looked at the chart. We know max gross weight's 2,950. So there is a little less weight, so that was going to slightly decrease our takeoff requirements. Headwind component COM. So we're not going to have to do any of that math, any of that sliding around for headwind and tailwind. It's just going to go straight over because it says COM winds. I got my piece of scratch paper in front of me here, so I'm going to try to write down some of those quick variables that's going to help us out. We said 4,000 feet pressure altitude. We said 2,800 pounds. And let's go see if we can tackle this chart. Okay, so we said that we're starting with standard temperature. So this says ISA, International Standard Atmosphere. We know 15 degrees is standard, but 15 degrees standard is for sea level. So if you was at 4,000 feet, standard is no longer 15 degrees. There's gonna be a lot of questions about that on the written exam. So if it says standard temperature, but you're at 4,000, well, snap, 4,000 feet, standard's not 15 anymore. We lose 2 degrees Celsius for every 1,000 feet, so it should be 8 degrees colder. What is that, like 7 degrees maybe? So we could do that math, but we don't have to, because in this example, it says ISA, International Standard Atmosphere, and here's our line. So we need to find where our International Standard Atmosphere intersects 4,000, right here where my mouse pointer is. But to try to make it easier, let's see if I can do some drawing. And I might be able to actually draw. We don't use red because they already used red. You guys want to be purple people? Here we are, we're purple. So we said 4,000 feet on standard, that's where we're at. I'm gonna click, and I'm gonna try to do my best to come straight over. Okay, so that's where I'm intersecting the next reference line. If I was max gross weight, I would just keep going straight over. But wait a minute, it says we're at 2,800 pounds. So we intersect this reference line right about here, which is barely beneath that big fat black line. So we need to follow that big fat black line, the slope of it down to 2,800 pounds. Maybe something like that. And unfortunately, even the smallest little change is going to affect your end answer. But there you go. So I just made the change that's going to decrease our takeoff requirements because we're less weight. Now that I've made it to the appropriate weight, 2,800 pounds, I come straight over to the next reference line. I'm just about on this thick blue line here, I think. What a tricky little son of a gun. I tried my best, something like that. Okay, we're on wind, headwind, tailwind. Well, it said calm winds. So we're gonna try to just go straight over again. All right, now we're on 50-foot obstacle. And I can't remember, are we doing, no, we are, we're doing 50-foot obstacle. If the question asked for ground roll only, we would just come straight across and we'd say, hey, we need 1,050, 1,100 feet for ground roll. But this question asks about to clear 50-foot obstacle. So here I am on this reference line, this brown reference line, and now I need to go up and follow the same slope as the black lines. Maybe somewhere around here. And so I've found an answer. Here's 2,000 feet of runway required. Here's 1,000 feet. We're definitely above 1,500, but we're not quite up to 2,000, maybe 19, 18, 17. I get about 1,750, maybe 1,800, maybe 1,700, depending on how accurate you were with your math, with your sliding ruler. Okay, so we're thinking maybe like 1,700, 1,800, 1,750, somewhere in that ballpark. And I click, but it's not clicking. What am I doing wrong? Click, click. And that's how we got the answer of 1,750 for this performance chart. Any thoughts, questions, comments about that?
No, sir. I cleared up a lot of this stuff when it came to the weight changes. I was kind of confused about where to follow.
Okay, yes.
Factor in the weight. So that makes sense now to me a lot.
Awesome, cool. So well, good thing we went through this one. All right. So what other kind of questions do we have in this? We have some VOR questions. So VOR questions. Okay, so we can move on to some VOR questions. VOR, very high omnidirection range. And aviation is a building block process. It's a lifelong process. You know, like we try to teach you everything we possibly can in one semester and one whole college degree. I mean, gosh, there's so much about aviation. And one of the things that we're really wrapping our brain around right now is simple directions. There's 360 degrees in a circle. North is 360, south is 180, east is 090, west is 270. And these are some basic concepts that we've been going on together with the whole semester. So if you're still struggling with that information, then this VOR might seem a little more challenging to you. So the whole idea is that we are now working on VORs. It is a ground-based station. This ground-based station doesn't move, but we can analyze our current position in the air in relationship to that ground-based station. Okay. So in this example, we're going to use figure 24 and figure 28. And it says the VOR is tuned to the bottom VOR, and it says VOR TAC, VORTAC, area 3, and the aircraft is positioned over the town of Sulphur Springs, area 5. Which VOR indication is correct? So I guess I'll just walk you through this problem. That's what makes sense. And again, use your chicken scratch, use your notes. It says that we are tuned into the bottom, BONHAM, VOR. And we said that we are positioned over the town of Sulphur Springs. Okay. And then we could be using VOR 3, VOR 2, or VOR 5. So, you know, there I am. I just write out some really quick notes on my pad just to help me out. And let's see what our options look like. So here is a sectional chart, figure 24, and it says we are analyzing, there's what the VOR scope looks like. Well, I guess we'll look at this one first. Okay, so it says that we are trying to analyze the difference of VOR number 3, VOR number 2, or VOR number 5. So VOR number 3 has a full scale deflection to the right. There's no to, there's no from. We are analyzing the 210 degree radial, which is kind of the same thing as analyzing the reciprocal, which is the bottom, the 030 radial. This is a very tricky VOR scope. I hope that's not the one we're working on. And it is. Gosh. Well, unfortunately, you got to get through it, but this is kind of one of the more tricky ones. Okay, VOR scope 2, let's analyze that one. VOR scope 2, to from, TO, from, FR. In this example, there's a from FROM with a down arrow. So if you were flying an airplane and you saw this VOR scope, number 2 VOR scope, and it said 210 needle centered from. If you saw that in the airplane, 210 radial from needle centered, and you were analyzing the bottom VOR, you would find the 210 radial. So straight south would be the 180 radial. It's under my mouse, it says 18. And see there's a thick arrow right here. That would be the 210. So imagine that there's an imaginary line coming out of the bottom VOR, the 210 degree radial. Just follow my mouse. There's an imaginary line that comes straight out the VOR, 210 degree radial. That line is the 210 radial line from the station. If you are anywhere on that line and you fly a heading of 210, you will travel away from the station. So anywhere along that line is called the 210 from the station. There are two sides to every table, two sides to every coin, two sides to every VOR radial. So you could call it the 210 from the station, or you could call it the 0302 TO to the station, because anywhere along that same line, if you flew a heading of 030, you would travel to 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 the station. Interesting. Well, process of elimination, if we're looking at number 2, VOR scope number 2, and we're actually over the town of Sulphur Springs, where my mouse is, there's no way that's the correct answer. It's not VOR scope number 2. Well, we said we could have possible answers of VOR scope 3, 2, or 5. Let's see what's going on with VOR scope number 5. VOR scope number 5 shows 210 needle-centered TO. There's a small arrow pointing up, TO 2. So in that example, if the airplane was to fly a heading of 210, it would travel towards the station, which would be the same thing as the reciprocal down here of saying that we're on the 030 from the station. So to and from are reciprocals of each other. And in this example, number 5, the 210 to the station, it's really kind of difficult because it's not on the chart. So here's the VOR, the center of the VOR. If you're on the 210 TO to the station, you're actually up here where my mouse is, which is off the chart. And there'd be an imaginary line that travels in that direction. And if you're anywhere along that imaginary line and you flew a heading of 210, you would travel towards the station. Well, if we're over the town of Sulphur Springs, then you're not on a 210 to the station. So it's kind of a process of elimination for this particular question, why VOR scope number 3 is the best answer choice. I'll try to explain it to you. It's kind of a little tricky, but the idea is that the VOR scope really struggles when you're on a 90-degree perpendicular. When you are on a 90-degree perfect perpendicular, think of like straight crosswind, when you're on a perfect 90-degree angle from the VOR station, it gets confused. It's almost like a cone of confusion. Like when you fly right over top of a VOR scope, the VOR gets confused, cone of confusion. So if you're on a perfect 90-degree angle from the station, it doesn't know, it's confused. You're not in the correct to or from region. So in this example, the town of Sulphur Springs is really a perfect 90-degree angle away from any of those other possibilities, which was 210, 030. So Sulphur Springs is like a perfect 90-degree angle, and that's why the FAA is throwing this really dirty, nasty possible answer choice of VOR scope number 3, because you're not getting a to or a from. You're not getting a needle centered. You're not really getting any valid information from that VOR scope. So VORs are tricky. I don't expect everybody to be an expert about VOR. I would like to maybe try this next one down here. Maybe it might make more sense. Maybe this one down here will be a little better for us. Same idea. We're going to look at figure 24. And it says, what is the approximate position of the aircraft if the VOR receiver indicates 245 radial of Sulphur Springs, VOR DME, and 144 radial of Bonham VORTAC, area 3. So again, just pull out some chicken scratch, and we got a 245 degree radial of Sulphur Spring VOR, and that's area 5. And then we said we have a 144 degree radial of Bonham, area 3. So again, I just take some really quick notes so that way it can help me out when I'm trying to study my chart, keep all my thoughts straight. Okay, so this is called cross radial. So we talked about it for loss procedures. You can cross-check VOR. It's called triangulation. We don't need to be trigonometry math people, but you can be if you want to be. And the idea is that there's triangle math. I'm not trying to do triangle math, but I am trying to show you that if you know angles from two separate locations, you can pinpoint your particular location. Okay, cool. So we said that Sulphur Springs VOR. Here's the Sulphur Springs VOR, and there's the symbol right there in the center. It's got a square around it. That means DME, distance measuring equipment. So if it has a symbol with a square around it, that means DME, VOR, DME. Okay, so in this example, we are located somewhere on the 2, 4, 5 degree radial of Sulphur Springs. So let's use some of those tools we did earlier. Before we were purple people, that's fine. We can be purple people. So math, angles. Here's the 270 straight west. Here's south, 180. These are oriented towards magnetic north because you're using your magnetic compass. Okay, so 270. Here's a really thick number right here. So that'd probably be the 240. We said we're the 245. So probably this line right here. So from the center of the VOR station, and let's see again. So here's 210. Here's 180. There's the 270. We are hunting for the 245. Here's the 240. There's the 245. So let's just draw this line out, and we're somewhere along this line. This is the 245 radial from the station. So if you are anywhere along that line, you can center the needle and it will center on 245 and the arrow will say from, FM. So anywhere along that line, you are located on the 245 radial from the station. If you were anywhere along that line and you flew a heading of 245, you would travel away from the station. The 245 radial from the station would be very similar to the 065 to TO, to the station, where if you flew a heading of 065, you would travel to the station. So the needle could center with a TO indication for 065. Okay, I got something flashing here. Maybe somebody's trying to talk. Let's see. Oh, Dylan got bumped out. He's trying to get back in. Okay, so we're talking about VOR radials, and we have drawn the 245 radial from Sulphur Springs. We are somewhere along that line. Okay, now we're going to use a second VOR. The problem in question said the 144 radial, off of the Bonham VOR, area 3. So up here, they have, I don't know, my mouse just, here it is. Okay, so here's area 3 and here's the Bonham VOR. So here's the center of the VOR. Click. Okay, so there's the 120 radial. There's the 150 radial. This would be about the 140. This would be about the 145. We said we're the 144. So anywhere along this line, okay, I did my best. There it is. So we have just cross-radialed two VORs. And where those lines meet is our location. So loss procedures or cross-checking VORs, you're going to be an instrument pilot someday. You got to start learning instrument pilot stuff, VOR. You are located somewhere right around here because Sulphur Springs VOR said you're located on the 245 radial. The Bonham VOR said you're located on the 144 radial. Those are both from the station. So you are located right around here somewhere, which puts you really close to this R in a circle, PVT. It's a private airport named Glenmar. So if I click, go back, there's the answer. You're located at Glenmar Airport. VOR. So I just cleared those. And I could do more VOR questions, or we could move on to something else. I say we keep moving then. Nobody's really speaking up. Here's another problem that's involving some math, some flight planning math. It says you're on a cross-country flight. You're at point A at 1500 hours. The plan is to reach point B at 1530 hours. You've got the following information to determine the indicated airspeed required to reach B on schedule. So the distance between A and B is 70 nautical miles. Forecasted winds 310 at 15 knots. Pressure altitude is 8,000 feet. Ambient temperature is -10 Celsius. True course is 270. Okay, so what do we really need to know? We know that we crossed point A at 1500. The plan is to reach B at 1530. And we have, I guess I don't need to write all this down because we don't need to flip between figures and charts. I can just keep it all in the same picture. Okay, so let's use our tool. We're texting. And what do we know? Knowns and unknowns. We know that there's 70 nautical miles to go, and we have 30 minutes to get there. We know the wind. Let's keep reading it. We know we got to figure out the direction though. On a cross-country flight, point A is 1500 hours. The plane is reached B at 1530. Use the following information to determine the indicated airspeed required to reach point B on schedule. Oh my gosh, are they trying to throw us off? Okay, I see, true course. Okay, so 30 minutes to get there. Our course needs to be our true course. Okay, our true course is 270. It's already written there, but I just got to write it up here. Course is 270, but the wind is 310 at 15 knots. Okay, so let's think about that. Some of those basics that we talked about before. It's gonna kick me out, but that's okay. All right, so the back of your whiz wheel is like a compass. So like at the top, see I have like north, and then over here I have west, and then I have east and south. So the best thing I can do is tell you to read the whiz wheel. So the instructions are literally written here at the top. You know, step 1, place wind direction under true index. We said that the wind direction, so here's the word true index. We said that the wind direction is 310. So I spin the inner wheel to line up 310 with the true index. And then it says that the wind is 15 knots. Well, in the center of your whiz wheel, there's a circle. They call that a grommet. And so what you're going to do is you can line that grommet up with any number that you want to, and then just mark up 15 knots. For me, I like to line it up with a good solid reference number like 100. It's a good solid reference number. So now that I got 100 lined up with my grommet, and I have 310 for my wind direction up the top, I need to make a mark. I wish I had a pencil. All I got is pen here. I'm looking around. I'm sure I have a pencil. And I'm going to take my pencil, and I'm going to make a mark. Oh yeah, we got a pencil. Don't you worry. So we're going to make a mark up 15 knots from that grommet, that center point. Oh yeah, that's a good looking mark right there. Okay. So you can see that I have put a pencil mark. I drew a cross 15 knots up from the center grommet. I lined up my center grommet with 100, and I put a cross about 15 knots up to mark my spot. Okay, that was step 1. Place wind direction under true index. Step 2, mark wind velocity up from the center. That's what I did. Step 3, place true course under true index. Okay, so the problem said that our true course is 270. So now here you are in your true index, and I need to spin that sucker to line it up with 270, which is west. There she be. She's lined up. 270 lined up with west. Okay. Number 4, slide wind velocity mark, that mark you just made, to the true airspeed line. And we don't have true airspeed information. And then you can read the ground speed under the center. And then you can have wind correction angle between the center line and the wind mark. So this question is making us do some backwards math. We've got it set up pretty well. What can we tell so far? How about that question? We can tell that, so if I'm looking at it like this, up, down, left, and right. I think it's a little backwards when the camera goes. So over here for me, that's the right side. Okay, so the right side is add. You add the wind. If the wind's from the right, you need to turn right to angle your airplane into the wind. If the wind's from the left, you need to turn left to angle your airplane in the wind. WCA, wind correction angle. Okay, so the idea is that the wind is from the right by about 5 degrees. So that mark that you see is about, so here's the center, and then it says 10, and then it says 20. It's about 5 degrees right. So we're gonna have, and also the mark is above, not below. So when the mark is above, that means it's a headwind. The wind is slowing you down. If the mark was below, it'd be a tailwind. The wind is speeding you up. So we got some information loaded up on our whiz wheel, but we need to do more math. We need to figure out the knowns and the unknowns. So let's go back to our screen and see what we can see. And this is what I kind of started to type up, but for some reason it kicked it out. So we said we have 70 nautical miles to go, and we have 30 minutes to get there. Okay, that's the information we needed. So I guess I'll go back. Sometimes I just got to write it down for it to make sense to me. We're going to use the other side of the wheel. Remember, time is always on the inner. Time is always on the inner. We have the knowns and the unknown. So what do we know? We know that we want to travel 70 miles, and we want to travel 70 miles in 30 minutes. So we need to set up that ratio on the front side of the wheel. We need to set up a ratio for 30 minutes, 70 miles. Time is always on the inner. So on the inner, so far, we've been focusing on that 60, that big arrow so much. But now we need to focus on the 30. We need to focus on 30. I about screwed up. You saw that. There's my 30. So we need to focus on that 30. We got 30 minutes, and we want to align 30 with 70. So I'm going to spin the wheel. And I can't do it in front of you. I just got to spin it. So 30 to 70. I want to align 30 minutes on the inner to 70 on the outer. I can't see it. There you go. Okay, so I got it lined up. 30 minutes on the inner, 70 minutes on the outer. Dang it, I said it wrong. 30 minutes on the inner, 70 miles on the outer. That is correct. 30 minutes on the inner, 70 miles on the outer. The ratio is set. Once you've set the ratio, move your eyes, not the wheel. So we're going to move our eyes. We want to know how fast do we have to travel, and how do we judge speed? by knots, nautical miles per hour. How fast do we need to travel? At what rate do we need to travel to achieve 70 miles on the outer with the 30 minutes on the inner? Well, we move our eyes, not the wheel. So I go and I check out moving my eyes to look at the 60 mark. Remember the big arrow? And it's dang near perfectly set up on 1.4. So there are no decimal places. 1.4 could be 0.14, 1.4, 14.0, 140, 1,400. I mean, whatever makes sense. So in this case, we are learning that if we travel at 140 knots, 140 nautical miles on the outer for 60 minutes on the inner, that would be what's necessary to achieve 70 miles on the outer, 30 minutes on the inner. So we have found the information we needed. We need to travel 140 knots over the ground, 140 knots ground speed. We need to achieve, so let me write that down. We need to achieve 140 knots KTS ground speed, GS, ground speed. Now that we have an idea of what we need to achieve, 140 knots ground speed, we can go back. And you can read through some of these directions. It's a little backwards the way we're doing it today. But look, it says number 5. It says read ground speed under the center. So in today's example, I'm going to put that center mark. And what you do is you slide. See how I can slide this whole sucker up and down? So I'm going to slide. So I got 140 under the center, which I'm just about dang near there, really. Close enough. So I'm at 140 under the center. That's my ground speed. So it looks like my X, my mark, looks to be just about 150. I'm doing this wrong. Gosh. I'm close. I really am. Oh, I spun out of place. See that? We're close. We're close on this one. It's kind of tricky. So I've done something wrong and I'm close. I wish I was better. They're not always easy. Let's look at you guys are seeing my screen. You're looking at it. Okay. On a cross-country flight, point A is crossed at 1500. The plane is to reach B at 1530. Use the following information to determine the indicated airspeed required. We think we need 140 knots ground speed. Distance between A and B is 70 nautical miles. The forecast wind is 340 at 310. Did I mark that correctly? 310, I did. At 15 knots, I did. Pressure altitude, 8,000 feet. Oh. This is a tricky question. So I'm thinking then that if we're traveling 270, if I want to achieve a ground speed of 140, I don't know. It says the correct answer is 137 knots, and I'm kind of struggling to figure out how they got that. I think maybe it has to do with pressure altitude of 8,000 feet. So the idea is that there's a rule of thumb for this. You can do math using the front side of the E6B, the whiz wheel. You can follow the directions here, and they have some math problems you can do. But roughly, we usually pick up about 2 knots of true airspeed for every 1,000 feet that we climb. Maybe that's a piece of the puzzle. 137 knots indicated airspeed. I don't know. My goal is not to waste our time, so I hate to just keep scratching my head in front of y'all, but something's tricky about it. And that's kind of like, one of the reasons why I really give you that advice that, gosh, some of these questions are just really tricky questions. and I will continue to work through this one. You know, maybe I'll have better answers on Monday or Friday office hours if anybody's interested. If anybody's been working through the problems and they've figured it out, but I've screwed something up somewhere. So all I can do is just be honest, you know. They say that's like, you know, one of the important things as an instructor. If you make a mistake, I've made a mistake somewhere and I can't quite put my finger on it right now. But you're learning about the whiz wheel. You're learning how you can follow the directions and you can input information on it. We're learning how to spin the wheel to get the information. You know, I think it's this simple. I'm overthinking it. Are you ready? I'm overthinking this thing. I already did the math and I told you the answer. The answer was 140. We needed to achieve the answer of 140. And the closest answer is 137. It's only 3 knots off. I think I'd just click that one and move on. There's probably some more elements to it. Goodness. Bad deal. Well, we don't have a whole lot of time sitting here in this class left. Our goal is to try to help you guys out, figure out more of some of these tricky questions that you might find on the test. Some of them are easier than others. How about this one? This seems like a pretty simple problem. This might be a good one for us to get through. So this one's really simple. Determine that your airplane is 90 pounds over max gross weight. How much fuel avgas must be drained to bring it within limits? So we all need to know that fuel weighs 6 pounds a gallon. So if you're, what am I doing wrong? You guys aren't seeing my screen right now, are you? So that's a piece of the problem. Okay. Okay, so now you're seeing my screen, and this problem says that we are 90 pounds over max gross weight. Too much. We can't take off if we're over max gross weight. It says how much avgas do we need to drain, and it says options. So if you're 90 pounds overweight, we know that fuel weighs 6 pounds a gallon. So it's simple as 90 divide by 6. And, you know, I think it's 15. I really do. But there's just something about math that makes me want to just dial it in the calculator, make sure we're not screwing something up. 15. So that's how you get the answer of 15 for that one. That one's a bit more simple. Clear drawings, X, stop share. Okay. Maybe there's some other simple ones we can grab over here. We got some weight and balance, which I think we did some of that the other day. Maybe not. Here's a, I got to share the screen so you can see them. This one's talking about weights and balances information. So which items are included in the empty weight of an aircraft? And you should know it's unusable fuel and undrainable oil. So if you're taking down notes, that'd be a good one for your notes. B is an incorrect answer. Full fuel tanks and engine oil to capacity. I mean, engine oil, yeah, that's a good answer, but full fuel is not. So you as the pilot, you know, if you want to take more friends and family flying, you can, but then you might not be able to take off with full fuel. So if that's the case, fuel is one of the weight and balance components that you need to account for. So it's almost a history lesson. Over the years, they've had different definitions. They've had something called standard empty weight, basic empty weight, licensed empty weight. There's a lot of different weights definitions over the years. Nowadays, we use a vocabulary word called basic empty weight. And basic empty weight, it includes unusable fuel, it includes undrainable oil. So those are just some weights that are going to be included in your basic empty weight. And then when you do a weight and balance math problem, remember WHAM, weight times arm equals moment. you have the weight, the basic empty weight of the airplane, and then it's already accounting those items. And then you just got to account for other weights like pilots, baggage, fuel. This will be our last problem here. You know, in the airplane, you guys maybe have been doing some ground reference maneuvers. You've been doing like some traffic pattern work, maybe some turns about a point, S turns along a road. And the idea is here that we're going to look at a rectangular course. And when would the aircraft turn less than 90 degrees? That's the question at hand. And it could be like corners 1, 4, 2, 4, 1, and 2. So in this example, you got a wind that's coming straight from the north. So like when you're here between corner 4 and 1, you're going to have a perfect headwind. There's no crab angle. Whereas here between 2 and 3, there's no, it's perfect tailwind. There's no crab angle. But wait a minute, when you're flying the leg between number 1 and 2, you're going to have to crab angle. You're going to have to deflect your airplane to the right. You're going to have to angle the airplane to the right to account for the wind. So when you're going between number 1 and 2, you're going to have a heading that is to the right of 270. Same thing down here. When you're flying between number 3 and number 4, you're going to have a heading that is to the left of 090. Okay, so during corners, during current corner number 4, you're going to already be angled to the left. So it's going to be less than 90-degree turn on number 4. On number 1, you're going to be on a straight heading to north, and you're going to turn less than 90 degrees to be able to travel west. On number 2, you're going to already be angled something to the right of 270. So by the time you turn left to get to 180, you're going to have a greater than 90-degree turn for number 2. For number 3, you started on a heading of 180, and you're going to have to turn to something to the left of 090. So that's going to be a greater than 90-degree turn. Our question asked, when would the aircraft be turned less than 90 degrees? Well, the answer is going to be number 4, because you're already be angled at the beginning of number 4. So number 4 is a correct answer. Number 1 is the next correct answer because you're not making that full 90-degree turn because of the wind. So the answer is to be 1 and 4 on that one. So, I mean, I see that we're out of time. My goal is not to keep anybody over. I tell you that, you know, there's lots and lots of questions in that test bank. We're just not going to be able to go through all of them. I'm happy to answer any questions now. If anybody wants to ask any questions before they head out, I'm happy to help out during my office hours on Friday, 9 to 12. I'll have one more session. It'll kind of be an optional if you want to log in for it on Monday. And we can go over some more questions before the final launches Monday afternoon, say 1 p.m. If there's any thoughts or questions, I'm happy to entertain them. I'm not trying to hold you up if you have to head out.
All right, thank you.
No, thank you.
All right. Have a good day.
Hey, have a good day.
Have a good day.
Thank you, sir. Have a good one.
Thank you.